You've heard of gradient descent, but have you ever wondered how it actually works? Here's the simplest way I can explain it. Gradient descent is an optimization algorithm that helps neural networks learn by minimizing the difference between their predictions and the actual outcomes. The key insight is that it does this by iteratively adjusting the model's parameters to reduce the error, kind of like how you might adjust the settings on a camera to get the perfect shot. Think of an embedding like a library where books rearrange by meaning, and gradient descent is the process of finding the perfect arrangement. Now, I'm not 100% sure about the exact math behind it, but my read is that it's based on the concept of calculus, specifically partial derivatives. Honestly, the math can get pretty complex, but the idea is that gradient descent uses these partial derivatives to compute the gradient of the loss function, which tells the model the direction it needs to move to minimize the error. And this is where it gets interesting. The model then takes a step in that direction, and the process is repeated until the model converges on the optimal solution. Stick around, the number of iterations it takes to converge is wild. Let me walk you through how I got here, and we'll dive into the details of how gradient descent is used in popular models like BERT and transformer architectures. So to understand how gradient descent works, you need to know about the history of optimization algorithms. Look, the concept of gradient descent has been around for decades, but it wasn't until recently that it became a crucial component in deep learning. Honestly, when I first saw how gradient descent was used in neural networks, I thought it was kind of like a game of hill climbing, where the algorithm tries to find the lowest point in a valley by taking small steps in the right direction. The key insight is that gradient descent uses calculus to compute the gradient of the loss function, which tells the model the direction it needs to move to minimize the error. Now, I'm not 100% sure about the exact math behind it, but my read is that it's based on the concept of partial derivatives. This part is actually kind of funny because, when you think about it, gradient descent is essentially a fancy way of saying, try a little bit of this, see if it works, and if not, try a little bit of that. And this is where it gets interesting. The model then takes a step in that direction, and the process is repeated until the model converges on the optimal solution.
The architecture here is fundamentally different from traditional optimization algorithms, as it's designed to handle high-dimensional spaces and non-convex functions. So, to give you a better idea of how this works, let's consider a simple example. Imagine you're trying to find the lowest point in a valley by taking small steps in the right direction. Each step you take is like an iteration of the gradient descent algorithm, where you're trying to find the direction that leads you to the lowest point. Wait, what if the valley is really complex, with lots of hills and ridges? That's where the magic of gradient descent comes in, as it can handle these complex landscapes and still find the optimal solution. I mean, it's not always easy, and sometimes the model can get stuck in a local minimum, but that's a topic for another time. The point is, gradient descent is a powerful tool that has revolutionized the field of deep learning, and it's still an active area of research. Here's the simplest way I can explain the evidence for gradient descent. It's all about the numbers. Look at the benchmarks for popular models like BERT and Roberta. They've achieved state-of-the-art results on a wide range of natural language processing tasks. For example, BERT's DevSet score on the GLUE benchmark is around 80.5, which is significantly higher than the previous state-of-the-art. Honestly, these numbers are impressive, but what's even more interesting is how they were achieved. The key insight is that gradient descent is a crucial component of these models' training processes. By iteratively adjusting the model's parameters to minimize the loss function, gradient descent allows the model to learn from its mistakes and improve its performance over time. Now, I'm not 100% sure about the exact math behind it, but my read is that it's based on the concept of partial derivatives, which are used to compute the gradient of the loss function. So, let's consider a specific example. Over at Google, the researchers behind BERT reported that they used a variant of gradient descent called AtomW to train their model. The results were stunning. BERT achieved state-of-the-art results on a wide range of tasks, including question answering and text classification. Compare that to what Meta reported for their own language model, which used a different optimization algorithm. Same quarter, NVIDIA announced their own language model, which used a custom-built optimizer that outperformed AtomW in some cases. Look, the architecture here is fundamentally different from traditional optimization algorithms, as it's designed to handle high-dimensional spaces and non-convex functions. The benchmarks are impressive, but here's what they're hiding. The models are still prone to overfitting, especially when trained on large datasets.
I mean, it's not all bad news. Researchers have been working on new techniques to regularize the models and prevent overfitting. And this is where it gets interesting. The models are not just getting better at recognizing patterns, they're also getting better at generating new text. Wait, what about the computational cost of training these models? It's not cheap, let me tell you. Look at the numbers, $2.7 billion in 1 quarter. That's up from $400 million 2 years ago. Honestly, these numbers are staggering, but what's even more staggering is the fact that the cost is still decreasing over time. Now, I'm not 100% sure about the exact reason behind this trend, but my read is that it's due to advances in hardware and software.
The key insight here is that the computational cost is not just a function of the model's size, but also its architecture. Some models are more efficient than others, and that's what makes them more suitable for real-world applications.
So, what does this mean for the future of natural language processing? Well, for one thing, it means that we can expect to see even more powerful models in the future. But here's the part that really got me thinking. What if we could use gradient descent to train models that are not just good at recognizing patterns, but also good at generating new ideas? Here's the simplest way I can explain why gradient descent matters. It's all about the real-world impact. If you're a developer, this means you can build more accurate models that learn from their mistakes, and that's a huge deal. For anyone using language models like BERT or Roberta, here's what changes. You get better performance on tasks like question answering and text classification. Now, I'm not 100% sure about the exact timeline, but my read is that by Q3 2027, we'll see even more widespread adoption of gradient descent in industries like healthcare and finance. Look, Misa, the key insight is that gradient descent is not just a tool for optimizing models, it's a fundamental component of how AI systems learn and improve. And this is where it gets interesting. As models get more complex, the need for efficient optimization algorithms like gradient descent becomes even more critical. So what's your read on this? I'm genuinely curious because I keep going back and forth on whether we'll see a shift towards more specialized optimization algorithms, or if gradient descent will continue to dominate. I mean, it's not like gradient descent is perfect, it can get stuck in local minima, and it's not always the most efficient algorithm. But, as
Notes, the benchmarks are impressive, but here's what they're hiding. The models are still prone to overfitting, especially when trained on large datasets. Honestly, I think the future of gradient descent is all about finding ways to make it more efficient and robust. Maybe we'll see the development of new algorithms that can handle high-dimensional spaces and non-convex functions even better than gradient descent, or maybe we'll see a shift towards more specialized optimization algorithms that are tailored to specific tasks or industries. Either way, it's an exciting time for AI research, and I'm excited to see what the future holds. The possibilities are endless, and it's up to us to explore them. Here's the simplest way I can explain what's next for gradient descent. It's all about refining the process. As we saw earlier, gradient descent is a powerful tool, but it's not perfect. I mean, it can get stuck in local minima, and it's not always the most efficient algorithm. So, what's the next step? Look, the key insight is that researchers are actively working on new techniques to improve gradient descent, such as using momentum or adaptive learning rates. Now, I'm not 100% sure about the exact timeline, but my read is that by mid-2027, we'll see significant advancements in optimization algorithms. Here's my call. By Q4 2027, we'll see the development of a new optimization algorithm that surpasses gradient descent in certain tasks. Come back and roast me if I'm wrong. If you want the deeper story on BERT and its impact on natural language processing, I did a full video on it, and it should be popping up on your screen right now. Watch that one next. If my call is wrong, tell me where. The best pushback usually changes my mind. The future of AI is all about pushing the boundaries of what's possible, and I'm excited to see what's next. Now let's see how this plays out.